Which path is shorter? Path 1 or path 2? Path 2, right? Well, how'd you know? You knew path 2 was the shortest because path 2 is 5 blocks long while path 1 is 10 blocks long. Clearly, because path 2 is shorter by 5 blocks, it's the shorter path. But what if you couldn't visually compare how long the paths were? Trees, fungi, and even our own cells are forced to solve this problem every day because they can't measure the length of any two paths. Despite this, plant roots, fungal hyphae, and our own blood vessels are optimized to produce the shortest paths from point A to point B. But this begs the question, how does nature build the most efficient network? And one of the most ingenious answers to this problem doesn't come from a human engineer. It comes from this giant single-celled slime mold, Physarum polycephalum, and despite the fact that it lacks a nervous system, it's become a practical model for how efficient networks emerge. Let's watch it solve this maze in real time. While it solves the maze, the slime mold is actually following a simple set of rules. Explore, reinforce, then prune. When exploring, the slime mold spreads tubes out in all directions, even to the dead ends and spots with no food. Why spend so much energy growing every direction? Without exploring, it can never discover a better path in the first place. The slime mold doesn't compare every possible route, and it doesn't pick the shortest path right away. So how does following this set of rules change the organism's shape? Every few minutes, the slime mold rhythmically contracts. These contractions push cytoplasm back and forth throughout the network like a heartbeat pushing blood through arteries. Now here's the important part. If more cytoplasm flows through a tube, that tube gradually widens. Because the tube is wider, even more cytoplasm can flow through. Meanwhile, tubes with less cytoplasm flowing through shrink as cytoplasm is directed elsewhere. When one branch connects to a food source, more cytoplasm flowing through allows nutrients to be transported back through the network more efficiently. In response, the pattern of contractions changes so that more cytoplasm flows through the tube. Not only does this strengthen the connection, it also pulls cytoplasm away from less effective tubes, meaning those connections will shrink. This reinforces the fastest routes while simultaneously pruning the longest ones. Without ever planning out the network, the slime mold reshapes itself simply by redirecting its flow of cytoplasm. It algorithmically applies the same three rules again and again until only the tubes that most efficiently transport nutrients remain. So, do only slime molds follow this process? No, we can find the same rules in completely different biological systems. We can actually think of the process of slime mold growth and the process of blood vessel formation or angiogenesis as following remarkably similar rules. Spread tubes out in all directions, reinforce effective tubes, and prune those that are less efficient. Neither slime mold growth nor angiogenesis begins with a blueprint or a map. And oftentimes, nature doesn't solve for the shortest path by designing the perfect network from the start. It builds a rough draft, keeps what works, and removes what doesn't, and the result is the most efficient network nature can make.